everybody here, and thank you to the organizer. And so what I'm going to talk today is a work with a bunch of people that are enumerated here. Is Manuela Girotti from Emory, Bob Jenkins for University of South Florida, Guido Mazzucca and Camille Clausen that are in today, and Alexander Levina from Corteweg in University of California, and Joseph Najudan that is in Bristol, and Maximia Selle that is Italiana. Okay, so I'm going to talk about a set of big solution of PD with a large number of solitons, and then solution of PD with a random parameter where the soliton parameter are random variable. So this is the main topic of the talk. And so I'm studying KDV, and so as this pointed here, it was discovered in 1895, and after about 130 years, we are still studying it. So it's a very classical model, a fundamental model of shallow water, log waves in shallow water. And then there are many other integrable equations which belong to the family of one-dimensional nonlinear dispersive equation, which describes internal waves in ocean, acoustic waves, and so on. So what is a soliton in this case? So we have a nonlinear PD, and we do a classical traveling wave solution ansatz. So we are required that the solution depends only on one variable, which is x minus dt. You plug these into your equation, and you have two types of solution. One is localized, and is called soliton. So we have the set, and one is periodic. And it's still a traveling wave because, again, we have that the solution is given by one function of one variable, to x minus the velocity times t. So here, the feature of this is that the velocity is proportional to the amplitude, and it's described by one parameter, k. And so in this solution, we have two free parameters, the amplitude, the velocity, and the position, so the maximum of this wave. While in the periodic traveling wave, we have three parameters, so this constant beta 1, beta 2, beta 3, plus position, again, allocation of a reference point, a phase, we call it a phase. And the end here is the Jacobian elliptic function. So these are the two traveling solutions of the PDV which are bounded. Okay, so this equation has a feature of being integrable. It means it's the compatibility condition of two linear equations. One is this linear equation, and one is the third order differential equation. This is a symmetric operator, so for join this is anti-symmetric. And so the compatibility condition of these two linear equations that is written here, this linear equation can be written in this compact form that is a multiplication operator, not a differential operator, we get back KDV. Okay, so this was discovered about 1665, so long time ago. So the idea to solve it is you take your initial data, and you want to go on this linear space of, this is called also nonlinear Fourier transform. You map your initial data into a new set of variables, which are called scattering variables. You know them at time 0, and the game here is that this evolution in this set of variables is linear, so it's easy to evolve them, and then you do inverse scattering, and you come back to your evolution at time t. So in our case, we consider initial data which, decay rapidly at infinity or even step-like. So this formalism now is well developed for a large set of initial data. But what I want to consider is soliton initial data. So I'm considering initial data that decay rapidly at infinity or fast enough, let's say. And so the scattering data are characterized by the eigenvalue for the Schrödinger operator. So these are L2 function. So you have a set of L2 functions with eigenvalue like kappa j, and some norming constant that they call Pj. And then a reflection, a continuous spectrum, which is characterized by its reflection coefficient. So this is the data. Okay, so once we have this data,
Are you considering the decay initial condition?
Yeah, decay. So yes, now, sorry?
Step.
You can also consider step. I want to say that all these machineries were developed also for steps.
It does not decay.
Does not decay. Yeah.
But here in the
I'm doing only
decay.
decay. Yeah, but the machinery is developed for step, even oscillatory step. I mean, yes, it's a wide range of initial data for which the machinery works. Yeah, so in this setting, so if we have this, so this data, so I'm having my data, so the discrete spectrum parameterized by kappa j and j, and the continuous spectrum is parameterized by rho of kappa. Once you have this, we assume to have finite number of eigenvalue, which is the case when we are initial data decay at infinity. And so I don't want to enter very much on the condition. You need to have this setting. But so once you have this data, well, you write this function f, which is a kind of Fourier transform, it's actually a Fourier transform of your scattering. And this satisfies a linear equation clearly. And so once you have this object, you can solve KdV via a Fredholm determinant, which is given by this kernel, and identify the kernel with the operator kappa with the kernel. So the kernel kappa, which acts on L2 of x infinity, has an operator, which is anche a convolution operator. Okay, so is this given is this same function here, and we calculate in S plus C. Okay, so all this was developed a long time ago by Gelfand and Tamarchenko. So this is called Gelfand and Tamarchenko kernel, and was Dyson that realized that you can hook back a Fredholm determinant to something. And then there are several papers by Pope and Sattinger who developed the machinery for many equations, including the KT equation. Okay, so now if we have only one, so if you have no this non-continuous spectrum rho, so this.
So the parameters, kappa j is highs. So do they have some natural physical interpretation, or?
Yes, they are the amplitude. So they are the amplitude of the soliton. So these are kappa is the amplitude of the soliton. So and the isosceles. So yes, they are the amplitude. So
What you were giving was then like an end solid.
Yeah. You give an answer. Well, if you have a decreased initial data at infinity, the scattering data decompose soliton plus continuous spectrum. This is generic. So if you have sufficiently smooth condition, so you need decrease actually some decrease, which is faster than one of the lines. And then you have this decomposition. So this is generic. So this kind of data is generic. You have a bunch of soliton, not an infinite number. It must be finite, otherwise it will decrease at infinity plus some continuous spectrum. Okay, so now this is the setting, and if I want to have a rho equal to 0, this determinant, this Fredholm determinant becomes a normal determinant, and now is a matrix of dimension n which has these entities. So these chi j are positive, and the kappa j are all positive. Okay, here theta is just the contains space and time. So the dependence on space and time is only this exponent that you find here. Okay, so with one soliton solution already written, two soliton solution. I mean, here are two solitons that are, one is moving very slowly, one is moving a little bit faster. So this is a very slow soliton. Soliton move always in positive direction. And so the amplitude is proportional to the velocity. Okay, so we have the general formula that I've written here. So this very complicated relation, but if I look for a long time, so what's happened, so this is kind of mess, but what you see here is basically, apart from a very small time where the soliton interact, what you see here is basically two such, what you're seeing here. Okay, except when you have interaction. So, and indeed, if you look at for longer time, so the soliton solution decompose, I mean, you can look at t plus minus infinity. So if at t minus infinity is the sum of two sets, this is asymptotically, so up to exponentially small error. And plus infinity is the same formula, so the same set with the same speed. up to a phase shift. So the faster soliton is shifted forward, and the slower soliton, here kappa 1 is bigger than kappa 2, is shifted backwards. Okay, so this is the cycle. And so we can interpret, so this idea is to interpret soliton as point particles. So we have particles without velocity that interact, and after interaction, the only effect is to have a phase shift. So the faster particle we want is going to be down, so that at a certain time t, if you look, instead of being along the green line, is on the black line, and the actual phase shift is delta 1. And the slower particle is going to be up, so the phase shift is negative, and it's going a little bit backwards. So, okay, so this is a general fact. And so, so what are the basic properties of solitons? So they are localized traveling wave solution and the fundamental solution of KDV. And so the eigenvalues of the Lax operator gives the soliton amplitude and velocity, while the Norman constant is the position. And what we know from asymptotic analysis is that if we wait long enough, so even if we have a continuous spectrum, so after a while the solution decomposes soliton traveling on the right, plus a radiative part that is traveling backwards on the left, and decays at the rate 1/2 to the alpha, with alpha bigger than 0. And here we have a very rich zoom of value of alpha. So, I mean, it's typical of integrable system. So if you have higher order nonlinearity, the situation is much it's less rich, just 1/2. Okay, so let me say how the solution look like. So the solution, if you wait long enough, plus minus infinity, you have the solution, even if you start with, I don't know, a Gaussian initial data that look like a Gaussian, so it's far from being a soliton. The solution decomposes into a certain batch of soliton plus something small that goes to 0 at this rate. And the difference between plus and minus infinity in this soliton, so this is a raw soliton of amplitude kappa j, is the phase. So is the phase shift. So whenever every time a soliton meets another soliton, which is bigger, is pushed forward, otherwise it's pushed backward. And this gives the amount of which you have to push forward or backward. Okay, so now, so what I want to do is to study the behavior when you have a very large number of solitons, and actually I want to send n to infinity. And I call it a kind of solution soliton gas, and so the goal is to understand which kind of behavior they have this kind of solution. So it's a class, I mean, the way I'm doing the limit is a class of solution that gives a soliton gas. And then the second part of the talk, I want to consider a random configuration of a soliton and study how this random variable behave. So, and I have to select this Q, I mean, so this Q is interpreted as the limit as I'm going to infinity of this random variable. Okay, so let me start with some, so why we study this large set of soliton? Well, I mean, this is, has been, I mean, there is a whole recent literature in the last 10 years where people, I mean, so on average, you don't know the initial data when you study a lot of situations. So, and so the people decide to study large behavior of large set of solitons. That's, so you approximate dispersive equation with a lot of soliton because the radiative part of the data in any case is going away like at space 1/t to the alpha for some alpha. So the idea is to study the strongly nonlinear component of the wave. So these are, we are in the strongly nonlinear regime, and we want to see how things behave. And so here, so if you look in the xt plane, what this behavior look like is like a set of lines that intersect pairwise. So this is the crucial. So I mean, the typical intersection is pairwise, and every time there is an intersection, we have a shift. Okay, so let me say a little bit of literature when of solution with an infinite number of solitons. So there are Marchenko. So there are some results by Marchenko, and then there was that Zeistel, Witten, and Boyd. These three people consider, well, I mean, an infinite soliton solution where, I mean, you take the search function and then you replicate it by creating a periodic function. So this is interpreted as an infinite number of solitons to that equal distance, and this kind of solution converts to the elliptic wave of KdV. That's an anomaly. There is no dispersion limit of KdV. They also create, I mean, solution that contains an infinite number of solitons. So the number of solitons goes like 1 over epsilon, where epsilon is the dispersive parameter of the equation. Then there was a recent, I mean, a paper of 92 by Casey, Karkowski, and Zhao that we also create solutions with infinite number of solitons. And and they observe, I mean, so they were the first to observe that the solution, so you take infinite number of solitons, the solution, I mean, so if you take the sequence of kappa j in infinity, so the solution remains bounded by the highest eigenvalue. So you need to take this set of kappa j, so the Norman constant, so the eigenvalue in some interval, and you have a sequence, and then you can, so they prove in particular that the solution is bounded. This is not true for other equations like the focus of linear Schrödinger equation, the solution as an infinite upper bound. Then, another group of people who study infinite soliton limit was Zakharov and El. So this is in 1971 and 2003. And so they were interested in the interaction of a large number of solitons. And so this paper of Zakharov, 1971, is called Kinetic Theory of Soliton. And it basically studied the behavior of the interaction of a large set of solitons and introduced this equation that he called kinetic equation for a soliton gas. And nowadays they belong to the class of generalized hydrodynamic equations that have been introduced and studied by, Castro Alvarado, Bayona, Ricky Moore, and Herbert Spohn, and many other people. So, but what are these equations telling us? So, is that if you consider a very, very large set of solitons, and you want to, and you introduce the concept of soliton density, where this f of kappa xt represent the number of solitons in the interval x plus ds and kappa plus d kappa. So, then the velocity of the soliton with the spectral parameter kappa is deformed by so it's real velocity for k squared, that is the soliton velocity plus this integral equation, and the kernel is the kernel of the two soliton interaction. You can see. Okay, so this is the kernel of the two soliton interaction, and this soliton density satisfies a conservation law. So these equations are called generalized hydrodynamic because you have a conservation law and an integral equation. So this setting was these equations were first derived by Zakharov, but in the setting of the diluted gas. So diluted gas means you have the soliton far apart. And in the right equation where this V of kappa and V of S are replaced by the soliton velocity. So it will be 4 kappa squared, 4s squared. And then later, 30 years later, Gennady-El obtained this equation by deriving it as deriving a soliton gas as a special large genus solution of finite gap potential in the limit.
Good question. So the intuition for this, are these the phase shifts? These laws?
Yeah.
And so you're just kind of adding up all the phase shifts?
Yeah, it's exactly, yeah. So if you have your, so the soliton at time t squared, so if you take a time t, so the soliton position, the x should be 4 kappa squared, so it's the dislocation of soliton, plus 1 over kappa, and so the sum log of all the other interactions, kappa j minus kappa, so minus plus kappa j minus kappa, so sum over j, and then here you put the soliton velocity minus So this is a velocity times t, so times t, so this is a space, velocity times t is a space, and then you multiply by the density. So density times space is number, so this is a space. Then you divide delta x by delta t. So let me put and then you have your v of kappa, the actual soliton velocity, which in the limit becomes this formula. Kappa plus kappa, minus kappa. Sorry, this should be kappa. Yes, you're taking the kernel, and you know that every time you have a shift. It's basically the code. Sorry for interaction, yes?
The equation, but that takes 100 if your system class. Is it the person which parts of the scattering spectrum and it completely scattering?
Yeah, each of these dispersive equations has a soliton solution that they are interacting with the kernel. And for each equation, you have a kernel.
Yes, but it's topic language, it's not to scattering in the radiation and solitons.
It's possible, but I mean, so the effect of radiation is not much seen on the soliton side. So,
But
at this level, we don't see it. But another equation, we might see it. Yeah. Okay, so this experiment is 2016, and what they do here is they have a bunch of a very large number of solitons which are random. So amplitude are random and location are random. So they are put at separate distance, so you can distinguish them. And they throw a soliton over this large set of solitons, and they measure the velocity. And they verify numerically that this equation holds. So this is the cycle. So this soliton is called a tracer soliton, which run over what they call a soliton gas. Okay, so let me go to explain what I'm doing. So I mean, there are many ways we can take large set of soliton, and the way we are choosing is the following. So we started the inverse problem. And the inverse problem for soliton solution is the following. You need to find a vector m with has two entries. So this vector m as a function of kappa is a meromorphic function in the complex plane, which goes to 1 as kappa goes to infinity, and it has some residue condition, so satisfy this boundary value problem. So the residue, so it's a meromorphic function which has poles. And the residue condition are specified by this limiting. So here, so the spectral data enter in kappa j and kappa j and kj. And so we put a bunch of soliton between an interval I eta 2 and I eta 1, and we put them at equal space. So here theta contains space and time. So in this specific case, we have 4 soliton. And we want to send n to infinity. So to send n to infinity, I do the following. I put, my soliton on equal space in such a way that you get a uniform density between eta 1 and eta 2. And this is the way I choose the kappa. And the key, I'm rescaling. So I ask to be interpolated by a smooth function, R is smooth. So Tj is a function of kappa j, and it's divided by n. So I'm just scaling by 1 over n. So once you choose your spectral data in this way, the n-soliton solution has a very broad support. So as n is very large, the support is growing linearly with time. So you have a lot of soliton in an interval of size n. So it's a big solid. And then I'm sending n to infinity. And the limit, so with this limit, I arrive So I arrived to a jump matrix. Before I have a residue condition with a lot of poles, and now I have a jump matrix condition. So M is not anymore meromorphic in the complex plane, but becomes analytic with jump along two intervals. Okay, so this is the limit, and I consider, so this is my soliton gas limit of an infinite number of solitons. And the goal is to understand what this object, what the solution looks like. And the solution, so what we have done, I've taken the infinite soliton limit here. I can get the vol, and I want to know which kind of initial data I'm arriving to. So once I know M, once I construct M, the solution of KDV is just the one entry. And so the moment at infinity of the entries M1 of this infinite soliton limit. So the result, so the result is that Q of xt is can be again written as a Freidon determinant, now acting on the interval eta1, eta2 with this kernel. So R is the continuum limit of the Normin constant, and kappa and zeta are the eigenvector line between eta1 and eta2. So this is a Freidon determinant. And so what we get is that analytic property is that this solution is most dense, deterministic, so we don't have a randomness, and is in an infinity. So now, it's not, so it's step-like oscillator, basically. And the property, so the solution, so for this particular choice that we did, there are many other choices, is basically step-like oscillatory at plus infinity is decreasing exponentially fast to infinity. At minus infinity looks like an elliptic wave. What I want to remark is this error is all refers to the -1. And okay, if you want to do direct scattering with this data, is a very nasty object because the decrease is very, very slow. So this is a very bad beast to do direct scattering. Okay, so this is what we end up, and if you let the time go, so how this initial data behave is basically this fun. So is an oscillatory wave, then with regular constant oscillation, these are modulated oscillation, then exponential decrease. So this is a limit, so we consider this as a soliton gas limit of an infinite number of solitons with this kind of choice of scattering data. Okay, so the next step is yeah.
There is no randomness in where
It's not random. Not random. It's deterministic. I'm doing a limit. I try to see how to make a limit on the scattering. Now, so the second step is I want to put a big soliton on this stuff and see how it behaves. And so we put a big soliton because if you have a soliton, so if you have oscillation of the same on the same size, you're really not able to follow one specific peaks because when there are interactions, so if you take two solitons of more or less the same amplitude, they never cross. They exchange and they keep going. So it's very difficult to follow the speed of a soliton in this setting. So we need to put a big soliton and check how it behaves on this background. And so we call its peak the maximum, so the position of the maximum, and we follow it in time. And then we calculate the speed. And I'm not saying what these objects are, but are very, very explicit. So we calculate the speed of the soliton on the peak. And then we calculate the average over one period of oscillation. So here there are a lot of oscillation going on. And even if they are not proper oscillation, because are modulated oscillation, we can still identify a period. And so if you average this oscillation along a peak, you get what we call soliton average velocity, which is determined up to some error of order O to the t-1. And the result is that this average soliton velocity satisfies the Zakharov-El kinetic equation. So it's the average soliton velocity. Here F, so what are these objects here? So this F, so we have to interpret it as a soliton density, even so, we don't have a physical intuition why is the density, from the way we get it. because it's simply, so when you do this asymptotic analysis, you need to introduce a G function, which is defined in this form, where rho is to be determined. And so this F is basically the derivative with respect to X of rho. The group velocity here is the ratio of rho T over rho X. And in this, for this particular kind of solution, the continuity equation is trivially satisfied. Okay, so, but I mean, so this calculation, I mean, at least for me, was an understanding, I mean, so was kind of understanding what is this equation is about. So even in deterministic set, and it's not the soliton velocity, but it's the average. So it's the average soliton velocity. Because the soliton, when it crosses, it goes back and forward. So if you are going to cross a faster soliton take over a smaller soliton, the acquired phase, the acquired velocity, otherwise it can go backwards. So the soliton velocity is not, so is quite oscillatory. So, and this is the plot of the soliton speed. So we trace a soliton and we look at it behaves. So it's highly oscillatory, and the soliton velocity, so the average velocity is this one. Okay, so this is a magnifying plot, and now if we put the soliton over the gas, okay, we don't see oscillation here. So if you look at the scale, we don't see oscillation.
I understand the pictures, and maybe the one that came before with this sort of rarefaction. And so you're plotting time, and then what the oscillatory things are what?
The velocity, the x dot.
And then, okay, of a single peak.
Yeah, you take a big soliton and you look how it behaves right across of this soliton gas.
And earlier you had a slide which also had this sort of oscillatory.
Yeah, that is our soliton gas in the limit, how it behaves for a long time and goes to infinity.
But what was being plotted there?
The solution Q, the solution of KDV. So let me go back. This is the solution of KDV.
Oh, I see. Okay, so this was over space. Which is that a given?
X and I'm sorry, the review should be Q. Okay.
And the initial data that you're taking is literally a step.
Oscillatory step, because you accumulate a lot of soliton, and so I'm putting them basically at plus infinity, the solution is exponentially small, and at minus infinity is oscillatory. It's an oscillatory step. And in between, I don't know. I don't know what it is. So this is the limit of this infinite soliton, the way I'm taking it. I'm taking a limit and it's done this way. There are many ways to take anything soliton, so this is the way I'm getting to it. Okay, so yeah, so but that's what I want to say. This is the soliton velocity, and so if you look in a bigger scale, so you see a straight line. Okay, so this is a plot of all this stuff, but I mean, we are in a different scale, so we don't see oscillation. So this is the background, the soliton gas, so this solution of KDV, and this is the soliton running on it. This will be the free soliton velocity. This is the actual velocity, and if you zoom here in, so if you zoom in, you see this wiggle. But at a bigger scale, you don't see the wiggle. So this is Mark Hofer. So when I gave this talk, Mark Hofer gave me his experimental soliton gas result. So he gave me this plot where he put a soliton on a bunch of smaller solitons. I don't know how he did it, and he measured this oscillation of the velocity. So you also see experimentally the oscillation of the velocity. Okay, so but the message here is that the equation that satisfy the kinetic theory of soliton on this hydrodynamic type equation are the average soliton speed and the actual speed. That's the first message. Okay, so maybe 2 words. Probably I'm skipping on it. Let me skip it. So what I've done so far is a full description of a soliton gas, both in the time Dutch-British regime and in the space in the whole spatial domain. And I describe how a particle to a soliton interacts with the gas. And so far, I have only done something deterministic. So the idea is how to put randomness. And so the question is how to put randomness. And so the idea how to put randomness is the following. So I can take soliton with random initial data. I take the spectral parameter random, the norming constant random, and what is certain is that the expectation with respect to this random distribution does not solve KDD. So, I mean, what I can say about this quantity is that for sure does not solve KDD. So we want to study something that we could compare in expectation. And so the idea was, okay, we take a random scattering data. So I'm doing all the randomness at the level of scattering. So I'm taking some random scattering data. And so I know that the expectation of the random scattering data in the limit goes to infinity. So I take an infinite number of soliton. These expectations, so which I'm explaining a bit how to get, still solve a linear spectral problems that we can define a KDD solution. So you still solve a linear spectral problem. So what I'm doing, I have a scattering data here random, doing the scattering, I get a random KDD and soliton solution. Here I'm going down, I take an expectation of the scattering data in a certain sense that I'm going to explain. I'm going this row and I'm still get a soliton solution. So no, sorry, I'm not a soliton. I get a solution by construction. Because I mean this evolution is linear, so if you take expectation, we don't destroy the fact that the solution solve KDD. So the scattering data are associated to KDD solution. So the point is how to relate these two objects. So what is the relation between these two objects? And so the construction.
Sorry.
Yeah.
Can you kind of translate the random interpolation from the data to the original field?
Yeah, so you have scattering data, here random, you get a random and soliton solution.
Yeah,
Yeah.
but usually I think we want to start from the random initial condition of Q, right? Not this.
Yeah, but I'm doing the opposite.
Yeah,
I'm doing.
Can you kind of translate? Can you understand what kind of initial condition, random initial condition you're taking for Q?
Well, I mean, the point is, I mean, Q, I mean, so we are restricted to a soliton solution, so it's a soliton solution, so it's a finite dimensional phase space. And soliton solutions are finite dimensional Newtonian system here, so finite dimensional phase space. So you have random amplitude and random position substantially. You take a soliton with a random amplitude and random position.
From physics point of view, maybe we are interested in something like local equilibrium measure or something like that.
No, it's random position and random amplitude. That's so you are thinking of Fourier transform in this way, or?
No, in principle, but you can try to do inverse scattering for the measure.
Yeah, but that's very hard. No, that's much harder. If I give you this, go here and get something that doesn't mean. I mean, it's much harder.
Yeah.
So I mean, I can create something random here, do inverse scattering, and say, oh, what kind of random I guess here is a disaster.
Okay. Thank you.
Yes, it's a disaster. So I'm starting from something random here, I know how to handle, and I know how to do this. And so the point is that I'm getting something random here, I do the expectation, and this is linear, so you don't change. So this expectation, so if you do inverse scattering, still is a solution. So the point is how these two objects are related. And so what maybe let me, so probably, so let me explain what kind of randomness I put in. I mean, so again, I'm in the same setting as before. So I have a bunch of points to choose random. So, and I'm choosing them with some given distribution. So you choose them random in an interval. And the norming constant, I mean, could be random in principle, but to do the limit I want to do, I'm interpolating so a dependent variable of the kappa j. And this is again a sinus function. So this is the way I'm doing the randomness. So the kappa random, so I take random amplitude while the position are more deterministic. Or while they are random as a dependent, so once you choose the R, they are random to the point, but they are interpolated by a Smith function. Okay, now I do the limit, the continuum limit as before, so I do the limit minus equals before. But now, so so I choose two kind of randomness on the poles, so uniform distribution, or if you want to introduce, I mean, there are some issues here because if you have poles that are coincident, I mean, you have a singular solution of KDV, so you have to keep track of this. I mean, probability is almost very small, but I mean, you have still to keep track of the fact that they can overlap. And to avoid this, so we take as a Laguerre so that there is repulsion. This is so this is the position of the poles. And then, okay, so this is the limiting distribution of the Laguerre. So this is support on a compact interval, and the limited distribution of the poles is a uniform distribution in this interval where I choose to have my poles. And okay, so let me explain this. So the key feature here, okay, now I have, I mean, a Riemann-Hilbert problem, I mean, a pole condition, so to set up for the inverse problem. So I have poles in this random location, and I want to translate this pole into a jump. So this is a standard factor. So pole condition can be reduced to a jump condition for a certain matrix, and this is the matrix, and this is still the problem for the random gas. And then I do expectation. So this is what I mean to expectation of the scattering up. So I do expectation of this jump matrix in the limit n goes to infinity, and I arrive to a deterministic problem, which I call n infinity. Okay, so this is the setting. So we have two problems. One is random, and we have random and soliton solution. One is deterministic, and this is a soliton gas. So we want to compare these two potential, and so we have to study this error matrix. And this is, so okay, so this is a vector, but to do the analysis, you need to replace a vector with a matrix, but this is doable. And I mean, the fact that the key feature of this matrix now is that satisfy. So the key feature of this matrix is that satisfy a probabilistic, what is called probabilistic small norm argument. So satisfies small norm condition, and so it's under control, but on the probabilistic side. So there are sets where it does not satisfy, but I mean, the measure of this set goes to zero, as I goes to infinity. Okay, so basically the difference, so this is describes the difference. So E22 is the second entry of this matrix 2. So this matrix is basically 1 in probability. Okay, so the result then is the following, that so the QN, so the random soliton solution minus this soliton gas solution, the expectation goes to 0 as n goes to infinity. And so we have to look only at XLT that are before the log of n, so you cannot go too far, because the soliton gas live in a space of size n, so we can stay only in log n. And so there is a fluctuation. So the fluctuation, so Qn minus, so the soliton, the random soliton gas minus the deterministic soliton gas times n. So this difference is equal to this quantity plus a reminder. So this quantity is a linear statistic. So it's a linear statistic of a function which I call G, which is explicitly given as the entrance of the matrix n infinity, so the soliton gas. And it converges to a Gaussian distribution. So converging distribution to a Gaussian random value. Okay. So it means that basically all these quantities, so the fluctuation are Gaussian. So the fluctuation of this Qn minus Q are Gaussian random variable. And so let me stress that so at each point of x and t, so at each point of x and t, the variance depends on t. So we have at each point a Gaussian random value with variance that depends on x and t. Okay. So the correlation now, okay, so now correlation becomes basically correlation of Gaussian. can study two-point function of the difference and get the points of the correlation function of xgn, the Gaussian. So it's a little bit actually, it's quite different from what you get from design. Okay, so I think I'm done. So what we have done is basically we construct what we call a soliton gas. So an example of an infinite of a solution with infinite number of solitons, and we describe the interaction of the soliton gas with a bigger soliton, so something bigger that we can follow. And we call this interaction has been described in terms of the Zakharov-El kinetic equation. So what it would be nice to do is to get other configuration of what we call soliton gas and a more wider range of spectrum of randomness in particular. So we put randomness only on the soliton, but not on the norming, on the eigenvalue, but not on the norming constants. And so it would be nice to see a way to get also random norming constant and be able to predict it. And most importantly, I mean, so the derivation of this generalized hydrodynamic equation for the soliton and soliton density in the random setting, yes, remains an open problem. Okay.
Is it a GHD equation?
Yeah. Okay, so I think I'm done. So thank you.
Previous slide, you mentioned that you could obtain low large numbers and set a limit theorem.
No.
What about large deviation? No.
Not yet.
Not yet.
Yeah, no, so this is, no deviation. Well, but I mean, yes, yeah. So because so depends on the scale you are looking at.
Should be possible.
Yeah, so I mean, we are more focused on, so the time we are more focused on getting something, so this putting a soliton, this random soliton gas, and whether how value this can be.
The realization of the initial fields of the set of soliton gas one realization, then I do direct scattering. The spec would be wholly discrete, or would that also be a really component?
But what do you start with?
A realization of this you actually construct the random gas.
No, I mean, well, in the limit is continuous. I mean, so it's the spectrum is this band spectrum. Yeah, the limit is continuous. So in the limit, you have infinite number of solitons, you come out of L2. So we are not anymore in the limit, you go in infinities, we have step. So we have continuous spectrum. We go out of the class. It's a limit that goes out of the class.
To prevent Gibbs measure, so the minus B from the total in the initial field.
Thing, but you need, I mean, Gibbs measure, so this is a finite the soliton space is finite dimensional within the system, but the Gibbs measure is not normalizable, you have to put a cap.
Understanding the limit of infinity also essentially a finite density.
Yeah, but the Gibbs measure, you know, in the proper sense is not normalizable. So I just want to say the Gibbs measure, so the data. So I capital D squared, you're on the left, and then you have to take. So these are canonical variables. And so these lives in our class, and these lives in our nodes. Okay. And then we follow. So after this, so if you want to put this method. So this is unrestricted to soliton and soliton. So this should be. So now if you take your Gibbs measure, so you take a so now this is okay. This piece here is bounded because you have minus and capital to the 5. You're integrating over R plus. It's okay. But this is you need to integrate over all R, and it's about it. So let me call log Vj's here equal Vj. So this is your this Vj's. So this is it will be a natural measure to put on this finite dimensional integrable system when we do the limit values to infinity. Okay, so but I need to put a cutoff here because otherwise it's not convergent. So it means I have to put the soliton only in some finite window space.
And let's say you take the cutoff and then you scale the cutoff with the number of solitons.
Yeah.
And that it's possible to do.
Yeah, this is we didn't first. So yes, it's possible. Yeah, we didn't do actually. This is a very natural thing to do. We didn't. So there was some technical issue, but yes, we didn't do it. Yeah. This will be very natural. It's like coming to the work of family. It's like to consider finite toner and then send them to infinity. So now we put the soliton in a window and then send them to infinity and look only at the final scale. The only difference that the solitons travel only in one direction, so